Okay, we're good to go.
Thanks for organizing this, Jen. And yeah, if you've noticed the change in backgrounds over the last couple months, as you may recall, we were first styled in for my garage as we were in the process of relocating Re3D from our operations from Houston to Austin. We now have some of the team that's in the new facility, and I'm here in our East Austin office for those of you that have been there before while we're wrapping up the last of the little bits and bobs, and hopefully next month we'll all be together from our new facility. So we're so excited to give you a virtual tour, but we're more excited today to get to connect with all of you all. And I couldn't be more tickled because one of our Gigabot X2 users is actually my former alma mater, where I went to grad school and undergrad, University of Michigan-Dearborn. And they have just been doing really interesting things with their printer. So here today we have Dr. Chistopher Pannier, who's going to share a little bit more about their research. And they have an amazing lab. If you're ever in Dearborn, you should totally check it out with multiple other printers, a lot of fascinating research projects. So he can share more about their offerings if you're interested in being a student or a postdoc or collaborating with this amazing institution. So Chris, I'll turn it over to you.
Thank you. I'll share my slides. Okay, are the slides up?
Yes.
Comes up with my laser pointer. Okay, so I made a talk here titled Clog-busting fused granule fabrication. So we're having a little bit of fun with this. We're developing an intermittent fluidized bed for the Re3D Gigabot X2 at University of Michigan-Dearborn. And I'm using our university's template slides because our own project made the template. Here's one of our PhD students loading up tensile test specimens that were made on the Re3D Gigabot X2 for collecting tensile data as well as digital image correlation data to understand both the microstructure of the polymers and their overall mechanical properties. So in my talk today, I'll talk about our research group, our machine, and then we'll get into clog busting some of the feed throat clogs that we were experiencing when we started recycling our polymers on campus. And then we will finish up with a senior design team. Two of the members here are going to talk about the work they did to extend that solution to filament making on one of our other machines. So I work in part of the Sustainability Center at University of Michigan-Dearborn. We have 7 faculty members in 3 of the different departments. I've included a few here. Dr. Mohanty brings a material science expertise, and Dr. Ayub, who's on this call in our Industrial Manufacturing Systems department. I've got 3 students presenting with me today, Dawood, a PhD pre-candidate, Logan and Alex, who just finished their bachelor's degrees, and we're all in the mechanical department. So we received a Gigabot X2 XLT, one of the extra large and tall models. And we were in the beta group of receivers. So we have a Gigabot X2 beta XLT. The build volume on this machine is more than ½ a meter on the shortest axis, right? 3/4 of a meter, just about on length and height. So for a lot of 3D printers, you think of these as the overall printer dimension, but that's the build volume on this machine. And it's got an extruder that takes in pellets or granules, a form that looks like this, 3 to 5 millimeter size, and extrudes them into the bead of the 3D printed part. So you're skipping the filament making step when you print from pellets, granules, or flakes. This machine supports a range of nozzle sizes. And in this talk, we're going to use 2.85. So you might think of 1.75 as a common filament making diameter, or even 2.85 is a very thick filament diameter. We're using 2.85 to make the beads on this machine for the work that you'll see here. And then we can also go to a more traditional, like a 0.6 millimeter nozzle. So we're closing the loop on campus at U of M Dearborn. We're cycling PLA, polylactic acid polymer. So we have a machine shop with a 3D printing lab attached to it. So there's a whole fleet of MakerBot 3D printers. And the older MakerBots don't even have a heated build plate. So the students have to print a raft for every part they make. That means there's a lot of scrap PLA. When the students are making their parts and discarding the rafts, we've put in a collection system so we can take failed parts or excess rafts, collect the scrap, and then recycle it on campus, either directly as fused granule fabrication or by making our own filaments. So we've got a closed loop of relatively clean, not much contamination of these polymers, although color matching is a bit of an issue. With the capability of having the Gigabot on campus, we were able to have a student do an outreach project with our on-campus environmental interpretive center. Behind our campus is a River Rouge before it hits the Ford Rouge River factory. And in fact, Henry Ford once lived on an estate that's now on our campus. So there's this nature center that was looking for, more input from what's going on in our research labs, what's going on in our teaching labs. And we said, let's make some signage, let's 3D print letters and put up signs on the wall. So a student went through the process of learning how to get up and started on this machine, figuring out what appropriate infill and patterns were to make 3D printed lettering for the walls. And then if you get interested in this, feel free to ask me. We have a process to remove some of the stickiness, the residue from the glue stick that was present during printing, so you can get a smooth finish on your parts. We've also used our machine in teaching. I teach a mechatronics class at the graduate level, and a student team for their course project decided they wanted to use the Gigabot. So they were addressing the problem of a lack of a cooling fan for part cooling on our machine. And the students designed a new part and mounted a DC fan for cooling, for example, for PLA printing. When you print PLA, the glass transition temperature is quite low. It's about 60 Celsius. And PLA will crystallize while it's cooling. The crystallization happens most rapidly around 100 to 120 Celsius. So you want to get quickly from your printing temperature in the 180s to 200s down below 60. So you would want to use a cooling fan for the fastest cooling and the least crystallization. So the students hooked this up. Then they turned the fan on full speed and printed a part and ended up making a slinky. So this square tube that was made was printed with excessive cooling. And in that case, the layers didn't adhere together because the under layer was too close to the ambient temperature. So that's a cool thing. We didn't think you could make a slinky by extruding with a 2.85 nozzle. We didn't think about that option, but that's a cool application we came up with. So the question for the mechatronics students was, what kind of a thermal model do we need to use? What kind of cooling rates can we extract from the system so that we can design a feed-forward control approach to slice the part and then slice the cooling command and print with a cooling command specific to the motion that you're doing. It was a cool student project. And we're going to transition to our discussion of research that we're doing with this machine. And in fact, I've got a QR code for you. And the paper is available online for free as a link from the Solid Freeform Fabrication Symposium, the annual conference in Austin. And those papers all go up online free as PDFs. So this paper was titled Benchmarking the Tensile Properties of Polylactic Acid Recycled Through Fused Granule Fabrication Additive Manufacturing. And to explain the work that we did, I have Dawood Al-Napani.
All right. Hello, everyone. Dawood Al-Napani, PhD student at Dr. Pannier Lab. So usually often when we work with polymers and plastic, we ask ourselves, why can't we recycle these plastic forever? Why can't they recycle repeatedly? And that's because the material quality it has some limitation. And when we say material quality, we're referring at the limitation that recycling plastic has due to the material degradation. And that degradation could happen to multiple reasons. It could be exposure to heat or light or moisture, or it could be other factors as well. So in terms of this research that we're trying to do, we're trying to investigate these mechanical properties that will keep us informed about what exactly happened when we recycle multiple times, and also establish a benchmark data that can have and share with the community that use these kind of polymers in their processes. So for our research objective, again, we just wanted to quantify that mechanical properties, as well as we wanted to have a baseline of these data that can we base our future studies upon. So in the next slide, I'm just going to explain an overview of the cycle that we took in terms of the recycling process. So the first element in this process is material. So we have used virgin PLA pellets. That's between 3 and 4 size of pellets. And then next in the process, we dried these pellets in an oven at 45 degrees. And then after that, we printed the tubes that are like one walls of tubes using the Gigabot 3D, the Gigabot X tube. And then after that, because we wanted to do tensile testing, we had to prepare this material. So part of the preparation, we had to machine these, we have to cut these walls into 4 walls and machine these parts. Then we punch them into the dog bones. We did that in 2 orientation, the 0 degrees and the 90 degrees. And also we looked into the literature and we found out that if we just cut these walls and then punch them into the specimens, we would have these edges from naturally printing these walls, and then they might be presented as defects. So therefore, we had machined these parts. And as I've mentioned, we had 2 orientation. 0 is along the bead, 90 degree is 90 degrees from the bead. And then the further step, that's the mechanical testing that we did. But what I have explained, it's one pass of these of the polymer process. And I said that we wanted to do multiple passes. So during the 3D printing stage, we would take some of the material through the process, while most of the material will go back again into the recycling phase. Into the recycling passes, we would cut these tubes into smaller sizes, shred them, and then sieve them to the right size of granules for our process. So since we're speaking about sieving, for the sieving process, we have used filament reclaimer, which uses 2 processes of sieving, and printed several sieves that we printed in-house, has different dimensions, as I was showing here. So the largest sizes in the top, and then these sieves will be placed from the top, and then we would shake them side to side or up and down manually until we get to the desired sizes that we would like to use it for our process. Anything lower than 2 mm, we would just discard it or keep it aside for other recycling purposes as well. So here we have a process where we just wanted to make sure that our granules are within a specified limit that we wanted. We know that our 3D specified 3 to 5 mm pellets, and we wanted kind of to follow the same guideline of having our granules within the same size. This is the printing parameters that we have used. I'm just going to point few of these, but all of the details are in the paper as well. So we have used 2.85 millimeters nozzle, and the heating that we have used, it's kind of towards the higher end from whatever is specified in the manuals for PLA for the Gigabot. And one thing we had to do, which is we had to change the extrusion multiplier for our printing, because based on the slicer expected bead width, it was specified 3.4, and then as we are printing, we found out it was much lower than that, so we had to compensate or calibrate using the extrusion multiplier. And once we did that, we had achieved the expected bead width. Another thing that it was frustrating that we were running into errors while we were printing the tubes that we wanted to print. And when we tracked that code, we found out that the maximum extrude cross-sectional area default was 7, and we had to change the limit or raise the limit. So we're not faced with that error. So this is overall of our printing parameters. And then next, once we have these parameters and we had the granules, we loaded these granules and we were ready for printing, but we were faced with a challenge. I think it's been already discussed even in the last meeting that feeding was a challenge for most of us. So as we are loading these granules, we would have an intermittent clog in the system in the feed throat, and that would result into in some layers, or in the beginning it will be uniform and these layers would be good, but after that, because of that clog, the clog will maybe missing a layer, or because of that, these defects will be present into the printer that we're printing part that we wanted to print. So therefore, we were faced with a challenge, and we had to look into this challenge and see how we could solve that challenge. So we went all the way from manual tapping just on the feed throat, all the way to a vibration motor that we have used from like a back massager that was disassembled because it has the concentric weight, eccentric weight, so it vibrates. Another thing we have used even the drain snake just to clear all these clogs. And finally, we did the fluidized bed, which I will be talking about in the next few slides. That what solved our problem, and that's where we have resolved this issue of clogging. So here, what I'm showing is like the iteration that we went through in terms of modifying the design of the feed throat. So the first one, this is what we are seeing on the left. This is the original design. And then after that, the first 2 iteration, this is where we have used the vibration motor as it was placed outside or attached to the feed throat, and then it would vibrate to make sure that the feeding would be consistent. It was successful for most of the part, but there are some situation or cases where the clog will happen and we couldn't predict it. So therefore, we moved to the concept of using compressed air as the fluidized bed for our granules that's within the system. The picture, the feed throat that's in the white, we also tested multiple inlets where should the compressed air goes into our feed throat, and we found out it's the lower where it's best for our design. That's why we have finalized the design, and the picture on the far right, that's our design, our final design, where it has like a window. We can see exactly what's going inside this feed throat as well. So now this is how it looks like on the machine. And then that's the window I was talking about. So air would be coming in from the tube from the bottom, and then we would modulate the air, as I will be explaining in the next slide as well. So this is what the concept of fluidized bed. One of the iteration as well, we had first the clamp from the top attached to the main part, but then we have altered it, and we had it to be separate from the part, as we found that's more effective in our case. One of the challenges maybe I would like to talk about is the air sealing issue, because once we had perfected this design from there were no any more clogging in the system, we found out that there are some dust PLA particles coming out from the machine metal piece that we see from these areas, and we had to seal it to make sure that there are no dust coming out, or we're losing some air in that case from the fluidized bed that we have designed. So in terms of the fluidized bed control, we have the air supply that we are using from the building that's within our lab, and then we're controlling the flow, but we don't have a pressure regulator for this system. but we know that even though we said it's 115 psi, but it actually varies between 90 and 100, but it work well for our system. And then we have a ball valve that we are regulating open and closed based on our Arduino kind of design, where we have this cycle modulates on and off as shown into this time versus the valve being open and closed. So it will be open for a while and then we would close it. So it would modulate between open and close, and it will create that fluidized bed as we can see here. So the air would get into.
I would ask this before then, because we had already lost people. We had one person remaining, and I was like, well, she's gonna grad.
What is it?
Someone probably joined the call with their voice, their audio muted.
Okay.
Sorry about that. I muted that.
Oh, okay. All right. So anyways, then the air vents from the hopper from the tub, we would just loosen it a little bit to make sure that whatever compressed air in the system can be vented out from the hopper from the tub. And so once we solved all of this problem and we had now the fluidized bed in our system, we have implemented it. Now we have all the prints are successful, and we had, I would say, very close to 100% success rate using the system. But there is something I would like to tell her. We can see that for the first part we are printing right here, I was doing this print myself, so for the first half of the print, it was successful. So I went outside to have lunch. And then once I came back, all of these prints failed just because the motor massager was not reliable. But going forward, using the compressed air, all the prints were successful. So that's the story from the fluidized bed point of view. So now once we had all of these printed successfully, we moved into the tensile testing to look into these mechanical properties and before recycling and after recycling. So first we wanted to have these dog bone shape closer to a specific standard. So we have the ISO standard that we have used here, and it's very close to that standard in terms of the dimensions of the dog bone shapes. And then to produce these samples, we had these machine plates under like a press, and then we had a cutting like a die cutter that we have cut these PLA sheets into the dog bone shapes that we wanted to test with. And then once those were done, we had to do some tensile testing. And I just would like to give a little bit of overview about the stress and strain curve. Maybe most of us are aware of it, but just like as a refresher. So usually we have a ductile material that behaves the same as the curve on the left, where we have the stress and strain that has some plastic region and elastic region. However, the brittle material usually just break before getting, or as soon as it gets to the ultimate tensile strength. So whenever we say ultimate tensile strength, we're referring to this point right here. And then in the x-axis, that's where the strain at fracture, that's where the fracture happens. And then the slope that within the straight line, that's what the elastic modulus of the material itself. So keeping that in mind, we did all of these tests for the version, which is 0, and then first pass, second pass, all the way to the fourth pass of these recycling. And we looked at these stress and strain curve. And we were surprised because usually whenever you print to different orientations, the 0 degree and 90 degree, one would be kind of double the values of the other one, but here we did not see any significant difference between these two. One thing to mention that when we went to the fourth recycle pass, we noticed that the 0 degrees it's a little bit tougher than the 90-degree, but that's kind of the only thing that we have noticed from this experiment that we have done. So I'm just showing here the zero recycled again, and this is the fourth recycled for our process. So now we just put these like in the 0 degree and 90-degree in the same figures to look at if there is any trend or there is any whether increasing or decreasing in the strength or in the elastic modulus or strain at fracture. But it seems that it's just a statistical differences, and there is no major differences that can be noticed from these figures that we can see. So I just would like to summarize the project that we have done. We have solved the problems of the feeding that whenever we recycle using granules, using the Gigabot. And we also performed mechanical properties of these recycle passes, zero recycle passes all the way into fourth recycle passes. And we noticed that printing with 0 orientation or 90 orientation had the same strength, which we could take out and in consideration whenever we are designing different parts. So this is the end of my section. Now we are going to move on the senior design team that has designed a clog-busting filament production. And I have here Logan and Alex.
Hi, everybody. I'm Logan Dyrov. So myself and Alex both just graduated with our bachelor's in mechanical engineering, and we'll be presenting our senior design project. So we kind of took the compressed air agitation that was used in the Gigabot project and then extended that to the production of filament using recycled material, not simply printing with it. So this is the machine here, as you can see on the right, that we ended up working with. It's called the Noztek Xcalibur polymer extruder. And we wanted to improve the reliability of the system to make it more possible to produce usable filament made of recycled material. And we did this in 3 ways. So we looked at improving the hopper from the base hopper that we had by developing a compressed air agitation hopper, making modified extrusion nozzles at number 2 here to increase our mass flow rate of material that we get out, as well as changing the diameter of the extruded material. And then finally, we designed an air cooler or extruded material support that basically functions to both cool the molten material that comes out of the nozzle and provide some lift for it, as it can't support itself under its weight when it's extruded. So that kind of prevents it from pooling here, meaning we can stretch it and spool it up later on. And then just a brief overview of the polymer extrusion process. So in our case, the material will feed this into the hopper here at number 1. That would be our shredded material or virgin material, depending on what we're working with. And that shredded recycled material would be very similar to what Dawood had talked about in his presentation. And then that material is fed through the center here in the screw, and it moves through heater bands. These heater bands function to heat the material, melt it down, and then allow us to extrude it here at the die. And in our case, we'd be extruding through the nozzles, which is our die, of a circular cross section with a goal of getting 1.75 millimeter filament that's used commonly in hobbyist printing. So then I'll hand it over to Alex.
So as we can see in the original hopper that came with the Noztek Xcalibur, as shown in the picture on the top left, towards the bottom, we have converging walls, which is what mainly led to the clogging of material. And so our goal was to create 2 internal designs to kind of reduce the clogging and reduce the force that's collected towards the bottom. Our first design was the ramp, which is over here on the top right. And our second design is the Plinko, which was inspired by the 1980 game show Guess That Price. Hopefully many of you are familiar with that. We have also an air distributor piece, which is custom to both of the hoppers. So the air distributor will be placed beneath the hopper. The air distributor piece is meant to blow air into the hopper. So as you can see in the picture, these vents are actually pointed upwards. So as air is blown through it, it's directed towards all of the material. As far as hopper testing, what we did was we filled the hopper with pellets and with flakes, and then took compressed air from the wall and blew it into the hopper. And then this in turn created a fluidized bed, which then allowed the particles to settle. We used a solenoid valve that turned on and off. So as the hoppers are being blown and creating a fluidized bed, once the solenoid valve closes, the material was able to settle towards the bottom. Sorry about that. Everyone can see my screen, right?
Yes.
Okay. Okay, so as far as the nozzle design goes, we have 3 initial prototypes that we created. We have the 30-degree, the 45, and the 90-degree internal angles within the nozzles. The reason why we had to redesign our nozzles was because initially the Noztek Xcalibur came with a 3mm exit hole. However, we wanted to shrink that down to 1.75 millimeters to kind of fit more of a hobbyist and consumer needs. The material we used was brass because of its superior thermal properties. And then as far as testing the nozzle, what we did was we allowed the extruder to extrude for 1 minute. And then what we did was we measured the masses and compared the results. For our cooling system, we had 3 initial, is that showing? Okay, thank you. For our cooling design, we had 3 initial cooling systems. Our first one is on the left, which is the gray one. We had small holes along the bottom on each wall, but that was soon led to failure because the holes were too small, so air wasn't actually flowing out of there. So for our second design iteration, what we did was we increased the quantity of the holes and also increased the diameter of the holes. However, another design flaw that we had was that the back part, which you guys cannot see from this view, but was actually open. So a lot of air was flowing out of the backside. And in order to fix this, what we did was we added 2 ducts where the fans connected to. That way, the air is able to flow a lot more smoothly out of the holes. We also added a piece of sheet metal on the front. That way, melted polymer is not actually touching our cooling system. And then as far as testing, what we did was we added a piece of paper on the nozzle and allowed the cooling system to blow to kind of simulate what would happen when filament is actually being extruded.
All right, and then just to get a better idea of kind of the flow patterns that were established within our air distributor, we did some SolidWorks internal flow simulation. And as you can see here, my laser pointer real quick. So you can see here on the 2 side arms of the air distributor, you can see these vortexes form, these kind of spinning parts of the air, as well as in the central part here, you can see the 2 air paths coming in kind of converge and then stall to a slower velocity. And although this does happen doing particle studies and then as well as our physical testing, we did find that the air still makes its way out and can provide enough support for the extruded material, or in our physical testing for the paper that we had flapping in the wind there. And one thing that we determined might be a good modification to make in the future was maybe doing smoother transitions along these corners here, or potentially placing our blowers in different places so that we could have better airflow and better development of their velocity profile. And then for our final design, just to wrap up here, our hopper right here, we ended up going with the Plinko for both virgin material and the recycled flakes that we had. This had the least amount of clogs and was best for actually breaking it up with compressed air. For the nozzle, we ended up going with the 30-degree nozzle. It's had the best mass flow rate and stayed at a nice temperature for us. And then finally, we had our cooling system. This is a rendering of basically with the smoother transitions, more of a horseshoe shape. So hopefully that airflow in can develop more easily. And then something to know is that both the hopper and the previously shown cooling system are available at this QR code on our printable site. So they're remixable and able to be printed. So if anybody wanted to take a look at that, potentially print it on their own, that's available. And something else to note that we thought was pretty cool, we were able to take Best in ME at our senior design day competition, and just want to mention that. So it was a very fun project with Dr. Pannier and the rest of the lab. So I'll pass it back to Dr. Pannier for our conclusion here.
Thank you. So I think you, hopefully everyone has enjoyed seeing and learning from these. We've developed recycling capabilities at U of M Dearborn for both fused granule as well as fused filament. So taking the recycled material to make the filament. We found that the intermittent fluidized bed works well for both systems, for getting the right size granules to feed without clogging. And we're excited that we now have this capability up and running on campus. I'd like to thank you all for your time, and I do want to show that video. So I'm going to find a way to pause my sharing and get that video showing before we take questions. So, get my link set up. And then I have to share the right screen. And the mute button. Hopefully you can see the jumping of the granules or the stock pellets for the flowing system. Great. I'll stop that share and go back to the presentation. Okay, thank you.
We can't hear you, Samantha. Still no, I know. That was a really great presentation. Thank you all for sharing all the different presenters. So now if anyone has any questions, we can go around and talk about it. I am going to go ahead and stop recording the presentation.